To continue, now we have to Professor Luz de Teresa introduce to Professor Renato Iturriaga. Thank you, Luz. You can start.
Okay, thank you very much, Juan. Thank you, Renato. So Renato Iturriaga is a researcher at CIMAT in Mexico, in Guanajuato. He's not from Mexico City. So he worked in CIMAT. And he did, so it's a perfect person to talk here because he did his PhD in Brazil at IMPA. So since this seminar is like Brazilian, Spanish, Mexican, etc., he's also a representative from mathematics from Brazil. So he's also a member of the Mexican Academy of Sciences, and he was president of the Mexican Mathematical Society. He has a very intensive work also in diffusion of mathematics. I don't know if the word is diffusion, vulgarization of mathematics. He has written lot of journal of articles for the big audience in the journal Correo del Estado de Guanajuato. And he's an expert on dynamical systems, PDEs, and calculus of variation. So thank you very much, Renato. He's going to talk about homographic motions of the n-body problem.
Well, thank you very much, Luz, for the invitation. Thank you very much to all of you that are here. I am not so sure about that I am the perfect expositor for this. I think myself as an outlier in dynamical systems in a PDE seminar. So what I'm going to do is just tell a story. I will not go into many details, technical details, and I want to talk about these homographic motions of the n-body problem. So this is a joint work with Ezequiel Maderna and Eberto del Rio. So this is the plan. If I don't have a plan, then I tend to go very far away from what I wanted to do. So I want to tell you what is the n-body problem. I want to tell you what our homographic motions are. And then, so homographic motions is a special solution of the n-body problem. And we want to know what is going on in nearby initial conditions. And so this is the first variation equation we have to study. And I will explain this first variation equation and this very important property that in decoupling in invariant spaces. I think that's one of the main contributions. And then there are some applications. So the first application is instability. The second one is scattering. And then it's recovering and extending a result of Gauchot of last century, no, from 19th century. Okay, so basic notations for endpoints x1, x2, xn in RD. We will denote by capital X the configuration in RDN. And so we think of each point as a body, and each point has certain mass mi. And then Raj will be the distance between the bodies A and J. And we will always assume that the center of mass is 0. I mean, this is just a common thing. And so the n-body problem is just the second Newton's law plus the Newton's universal gravitational law. And so we have that the forces that for each body will feel the all other bodies, and this is just the sum. So the force that will feel the xi body will be the product of the masses, and with this, it is proportional to the product of the masses and the distance to the square. There's a cube there because there's this xj minus xi, which gives the direction. Okay, so this is Newton's gravitational law, and then seconds. Okay, and this force happens to have a potential. So there's this function which is a potential, and that means that the forces is the gradient of the use. And so second Newton's law just says that the mass times the acceleration is equal to the forces, which in this case is the gradient of u. Okay, so that's the n-body problem. That's a set of equations. And so, for example, if you have 3 bodies in the plane, this is an equation in 12 variables, and in this space is 18 variables. So very soon after 2 bodies, the equation becomes very, very complicated. And in fact, it is not completely understood, even for 3 bodies in the plane. Okay, so we will work only on R2. So what I want to talk is about a special solution, homographic solutions, homographic movements, that they have 2 ingredients. They have something like the 2-body problem and central configurations. So the 2-body problem is the ones that we learned in the primary school, that we have 2 bodies and they move in ellipses. In general, they are conics. And so this problem was solved by Newton. And okay, so that we understand. Central configurations. So this is the following. We define for each configuration the inertia. The inertia is this quadratic function, which is positive definitely. No, I mean the masses are positive. And so it's kind of an ellipsoid. It is a sphere if the well, I mean an ellipsoid. What do I mean? The inverse values of a constant. So the energy level, the surface levels of these are ellipsoids, or a sphere if all the masses are equal. And precisely, critical points of the potential restricted to this sphere will be called central configurations. So that means that the gradient of u is proportional to the gradient of I, and the gradient of I is so what it means is that the acceleration is in the same direction of the position. No, so this gradient of u is like I told you before. The gradient is the acceleration times the masses, and here we have the masses coming from here. Okay, so we have central configurations means that the acceleration is in the same direction of the position. So if you have a special configuration, like that satisfies this, and you just leave it alone with no velocity, this will just collapse to the center of mass. Okay, so homographic solutions are solutions that the fact is that if you have a central planar configuration T, so this is just a configuration, and then you multiply this T by zeta of T, a solution of the Kepler problem. So what I want to think of this is this T is contained in R2N, and then zeta is, and R2N is just like Cn, and this is kind of a complex multiplication of in each entrance. So what is really happening is that you have the central configuration and you are rotating the configuration by the argument of C, and then you are making an homothetic thing, contracting or expanding by the norm of C of T. So the solution of the n-body problem is just the same central configuration rotating and becoming bigger or smaller. So you have, and then zeta of T is solution of the Kepler problem. So you have basically two options, or it's an ellipse or an hyperbola, or in particular, it could be a circle, or also in the middle, a parabola. Okay. And so this is what's going on. The equation is the following. No, it is a solution, so it satisfies this. And we want to know what's going on around the solution that we know. So what happens is that very few solutions are explicitly known in the n-body problem. One of these is these homographic solutions, and we want to understand what is going on nearby these solutions, and so it is very natural to study the linearization. So this linearization, well, this is the linearization of this equation. So this is a second order differential equation, linear, depending on time. And so we want to study this equation. Okay. So just let me put some notations. The space, there would be some particular space, K. So given any configuration, Kx will be the subspace of configuration similar to X. So this is what I was talking about earlier. So the space R2N can be thought as Cn, and Kx is the complex one-dimensional linear subspace generated by the configuration X. So you take X and you move it with a rotation and with an contraction or expansion. So in particular, if X is a central configuration, all configurations in Kx are also central. And so all the orbit of an homographic configurations are central configurations. So the homographic is really the homographic solution. It is around the space K. Well, it is contained in the space K. But of course, we want to, when you move the initial solutions nearby, you will go out of the space K. So there is this new metric that we want to define. And so it is, so I will call it the weight metric. So a weight inner product. So we define the weight inner product as the usual product, just multiplying by the masses. And so the gradient of a function depends on the inner product. And so the gradient with respect to the weight metric will be the standard gradient divided by mg. And also the Hessians in each row, well, in each pair of rows, you have that the Hessian will be 1 over mj, the usual Hessian. Okay, so this is a new metric. What is important is that the second differential form, which really depends on the metric also, in this case, we have the same differential form. And the differential form is given by, well, just this formula. Either you calculate the Hessian in the metric M, and then you with the inner product in the metric M, and this turns out to be the Hessian in the standard way with the standard point y in the standard one. So I mean, in the Hessian you are divided by mj, and in the product you are multiplying by mj, so this cancels. No? So it is the second differential form are the same, but you have different endomorphisms for the Hessians. Okay, so and the equations look very nice here. So it is just like the m disappears. No, it's like the acceleration is equal to the gradient, and the linearization also becomes. I mean, you lose the m's, and okay. But so what? I mean, this looks nice, but it is. I mean, it's kind of useless if you are just doing this. The point is that in a central configuration, the acceleration is in direction of x. So the gradient with respect to the weight metric is the accelerations. So for all points in K, the gradient is also in K. And that means that, therefore, the endomorphism of the Hessian with respect to metric M leaves K invariant. And hence, since the Hessian is symmetric with respect to the weight metric, it also leaves invariant the orthogonal complement in the metric M of the orthogonal complement to K. So that means that the Hessian leaves invariant K and also the orthogonal complement T. And this means that the linearization decouples. And this is very important because you have, I mean, as a general rule, it is easier to solve two linear equations in less variables than one linear equation in more variables. But moreover, you are decoupling the space K where there was some kind of degenerated. So the Hessian in K is kind of degenerated because it is where you have all kind of symmetries. Okay, so you have the equation decouples, and so the application number one is the instability. And what think and have in mind the following central configuration. It is known by since Lagrange that the equiliteral triangle is a minimal configuration no matter what masses you put in each body. So this was known by Lagrange. It was discovered by Lagrange. And I will be mainly thinking in that example. But in general, if we and that's a minimum central configuration. Minimum means that we were thinking of central configurations as critical points of view. Minimum will be minimums of view. And so we can hope that if we have a minimum central configuration, that this is, well, I'm sorry, this should be HUMXX. Oh, so I think I not right here. Am I right? No, I cannot write. Okay, so I'm sorry, this should be X and X, and this should be HM. So we like these to be positive definite. And in that case, it will be positive definites in all points of the orbit, because we understand how the Hessian behaves. It is invariant on the rotations, and it is homogeneous of degree -3 in homothesia. So if it's positive definite, it will be always positive definite. So in particular, if the Keplerian movement is an ellipse, this positive definite has a minimum. Okay, here again is with respect to M, both M's, but it doesn't matter because, as I told you before, it is the same for the standard metric. The second differential form is the same for the standard metric or not. Okay, so if we have this, what we prove is a Rauch types of theorem. The Rauch theorem is a theorem from geometry that is talking about if curvatures are, if you have two manifolds where you have an inequality of the curvatures, then you will have the Jacobi equations will grow faster than other ones. And this is a very similar theorem, and it is inspired by that Rauch theorem. And it says that if C is a non-trivial solution of the linearization, such that, well, sorry, this is C of 0 equals to 0, well, then X of T should be a non-trivial solution of the linearization, and you have a solution of the constant coefficients with the same initial conditions and with the same velocities. Then for all T, you have X of T, it's greater than C of T. I mean, this is a very natural thing, and it is strange that it is a little bit difficult to prove or difficult to see. I mean, in very colloquial terms, I would say if you have a Ferrari and you have a little car, and both are at the same time at 0, and they have the same initial conditions, then the Ferrari has a much more acceleration, and the Ferrari will be not far away than the bicycle. No, it is essentially that, and it is mysterious how this is not as trivial to prove than what you would imagine. Okay, so we prove something like this, and the consequence is that you understand pretty well the equations for the coefficient, for the constant coefficients. You have solutions that are growing exponentially, and so the linearizations, the Jacobi equation, has also exponentially growth solutions. And so this means that for the Poincaré map, the solution has eigenvalues with norm greater than 1, and this is the orbit is unstable. And that's it. No? Okay, so let me return with the hypothesis. To be minimum is a necessary condition, but it's not enough. And this was kind of a problem for us to understand this stupid thing that the restriction of the Hessian is not the Hessian of the restriction. No, this is kind of, you should learn this in Calculus 3 and never forget about it. And so what happens is that the triangle is it's a minimum of the restriction. So the Hessian of the restriction is positive definite, but that doesn't mean that the Hessian of the restriction will be positive definite. And so the second form of the inertia is involved, and it is not immediate that a minimum of the U restricted to E to I will be convex or positive definite. And for example, what happens in the triangle, this is a picture of masses. So you should think that this is the simplex of masses, and you should think as the corners where one mass is 1 and the other two are 0. You should think these edges as, well, one mass is 0 and the total weight is shared between two masses. And you should think of the center as the three masses being equal. And so the blue part is convex. And so our result applies to this blue part. And all the yellow part, we don't know what's going on. And so we conclude that for any eccentricity in this blue part, we have instability of the homographic motion. Okay, scattering. And so the second application is scattering. So let me tell you what is scattering. A solution is called forward hyperbolic if in R2N, if the solution behaves like a linear function. No, it just goes away with almost constant velocity. So it is, and you can imagine of this if you put the masses very far away and you kick them very fast and the masses are very little, for example. I mean, I'm just exaggerating, just to give you the idea that if things are far away and if you have a couple of flies far away, and then they go to infinity, and they will notice that the existence of the other flies. No, so they just go like linear velocity plus a little perturbation. So anyway, and this is to say that this is not an empty set, and you have this hyperbolic. Okay, and similar definition for backward hyperbolic, and by hyperbolic, if it's both, that you have a limit shade from the past and a limit shade to the future. So the scattering problem in just as in very broad sense is given an A minus and an A plus. Is there a bihyperbolic solution having these limit velocities? And so that's in the okay. So of course you have to put some energy restrictions. I mean, this is just in that generality is false, and you could add some energy restrictions, and then you can have you can find examples where that is also false. But but those are very particular examples. I mean, you don't know if there's an open and then sets of A minus and A pluses, which this is true. And that's probably true, no? That you can give an open set of n, open and dense, and an open and dense set of A pluses, such that you can find a hyperbolic solution. So we have a local answer to that. And the point is that, well, the set of bihyperbolic orbits is open, and you can define these functions A plus and A minus, and these functions are C1. This is a theorem of Maderna and Venturelli. So if you look at K plus and K minus, the kernel of these differentials, A plus and A minus, then kind of trivial application of the inverse function is that if K plus and K minus are transversal, then the scattering is locally true. So if you have a high bihyperbolic orbit and you somehow know this, that K plus and K minus are transversal, you know that you can find this scattering. Scattering, let me say that it is kind of also instability or hyperbolicity, no? I mean, that means that very near the point of A minus, you can find solutions that will go away to any point in A plus. So that this has the same spirit of instability. Okay, so let me talk about green bundles. This is an object borrowed from hyperbolic geometry and non-conjugate points. Okay, so 2 points x and y are conjugate if you can find a solution of the Jacobi equation. And here I am using Jacobi equation as a synonymous of the linearized equation. So 2 solutions of the linearized equation that will start in 0 and end in 0. And also, Maderna and Venturelli proved that hyperbolic orbits are eventually minimizers. So that means that they will not have conjugate points if eventually they will not have conjugate points. And this allows to define 2 sets or a subspace at the point, in a subspace in the tangent at the point x and x dot. So what do you want is, so this is the draw, so you have the orbit, and you have at the time t, where's the orbit, and you look for all the Jacobi fields that will vanish at the end. And you look for all the solutions that satisfy that, since the solutions are linear. This is a subspace. And if there are no conjugate points, you can prove that the limit of A plus the limit of A plus t as t goes to infinity exists, and you call it A plus. So what A plus is saying, at least as a first order approximation, of the solutions that will go to infinity to a point very near the orbit that you are looking. So, and K plus are also saying that has that kind of flavor. No, K plus are the differential the kernel of the differential of this function. So it is in the directions that this a plus doesn't change. So what we prove, I mean, this is the idea, what we prove is that a plus is equal to k plus. And moreover, if G plus is the subspace of bounded in the future Jacobi solutions, then also J plus is equal to A plus and K plus. And very similar to the negative for the past, for the negative. And so the transversality of K plus and K minus is equivalent to the transversality of E or J. And here comes an idea also. Well, okay. So the transversality of A plus and A minus is associated to the hyperbolicity of in the dynamical sense. And the transversality of J and J minus is equivalent to no bounded solutions in the past and the future. So, and turns out that a little convexity is enough to prove that there cannot be bounded solutions. So this little convexity will prove that J plus and J minus cannot intersect, and so they are transversal, and so that means that K plus and K minus is transversal. And where we can prove that this little convexity, well, in the same figure as before. No, for example, in the equilateral triangle, in the red circle, in the blue circle, you have this convexity, and that convexity will, I'm sorry, what I am talking about. So I am talking about a bihyperbolic orbit. And which is the bihyperbolic orbit? I take a triangle, a central configuration, but now what I take is not an ellipse, but a hyperbola. And this hyperbola will have these limits, and it is bihyperbolic. And I know that along this homographic motion, if I start with a triangle in this region, in this blue region, it will have the convexity that I need. So what I have proved is that we have an example where you have local scattering in the curve. And this is the first example of something that you have this local scattering in both in past and the future. Okay, how much? Okay. Okay, I have 4 minutes. So okay. This is an inspirational draw. This is the idea where I saw this draw something like 45 years ago, or no, 35 years ago when I was in the undergraduate, and it was part of my thesis or my final degree work. And it is a draw of Arnold and Aves, and it says something like, this is the Poincaré disk, and you have a geodesic, the red one. You have the orocycles, and there is this phrase that says that negative curvature is equivalent to strict convexity of the orocycles. And so the orocycles are these circles, and the transversality of the tangent bundle, you have to think this draw lived in the tangent space. And what this is saying, what Arnold said is, well, the transversality of the green bundles is equivalent to the negative curvature. And this, what is going on is the same thing, and it is very nice to have something that has been in your life for 35 years or something. Okay, so very quickly, recovering and extending Gauchon, and this is the part that is joined with Alberto del Rio. And so in the circular homographic triangle, you have this constant beta, or this parameter beta, depending on the masses. And what Gauchon proved is that the system is linear stable if and only if beta is less than 1. So it is something like this. It is the red parts. So Gauchon proved that in the circular case, when the ellipse is a circle, then you have stability in the red parts and instability in the yellow and the blue. What we prove is that we have instability on the blue for any ellipse, and Gauchon was talking only about the circle. So anyhow, it has this draw and the proofs. So Gauchon is a paper of comprendu, which only announces the result and details are lost in time. No, it is, so we don't know what Gauchon was having in mind. Then there is Ruth, recovers Gauchon, and in his paper, he says something like, well, I don't know where's the article of Gauchon. So already in 1875, Gauchon's work was lost. So now Guanajuato is impossible to get it. And Gauchon says something like, well, the equations are these, and we expand rejecting squares of small quantities, and after 10 pages of computations and calculations, he recovers Gauchon. More recently, in 2002, Roberts, he recovers Gauchon also, and these are words from his work. We carefully reduce the dimensions of the problem for 12 to 4. This is accomplished by eliminating standard integrals and then making a clever change of coordinates, which decouples the associated linear system. So I want to what should so this word decouples. Well, the decouple that he does is the same that we do, but in a very strange and difficult way, with a very clever and mysterious change of coordinates. And so this also takes number of pages of computations and things to prove it. And our work is, we have an immediate reduction of the second order differential in 2 dimensions, the equations in D, and then a straightforward change of variables to obtain a first order differential equation in 4 variables, which has this characteristical polynomial. And this is a polynomial which is very easy to solve, because I mean, you just change L squared by mu, and you have a quadratic one, and you can calculate the eigenvalues. And so for the system to be linear stable, you have that this should be imaginary. And so what is inside this first root should be negative, and this is negative is beta is less than 1. No, so you have -1 plus something little than 1, it is negative. And that's it. So, okay, so This change of coordinates works for any central configuration, so we expect more results, but we are not finishing that yet. Thank you.
Thank you very much, Renato. Now we open the micros for any question, or you can make the questions in the chat. Somebody? So if I understand, you make a change of variables that simplifies a lot the problem, and this ancient proof is recovered in 3 lines, more or less. I don't know.
¿Cómo? Dilo en español, porque no.
La prueba que ustedes hacen un cambio de variables que simplifica, desacopla las ecuaciones.
La prueba que hacemos, sí, lo que pasa es que desde el principio, desacoplas la ecuación. Y la desacoplas, no, por una razón muy simple, que es pues, que el hessiano deja invariantes 2 subespacios desde el principio, ¿no? O sea, las fuerzas apuntan, las asociaciones están en un lugar, están en el lugar del gradiente, y entonces el hessiano deja invariante ese subespacio, y luego como es simétrico, deja invariante el complemento ortogonal. Y eso desacopla las ecuaciones desde el principio.
Ya.
Y entonces, desde el principio, estás ya en una ecuación en dimensión 2. No tienes que reducir de 14 a 4 y hacer cambios de coordenadas muy no sé qué. O sea, inmediatamente estás en 2. Y eso, y entonces, y ahí haces un cambio de coordenadas más o menos estándar para la...
Ya. Pues,
que es cambiar el tiempo por el ángulo, y listo.
ya. Muy bien, se ve muy, muy bonito. Gracias. Felicidades.
Nada, gracias a ti. Gracias a ustedes.
More questions? Preguntas, comentarios. ¿No? Bueno, pues muchas gracias, Renato. Y sí, claro que entra dentro del seminario EDP Matemática Aplicada, y eso es aplicado o aplicable en su origen, ¿no? Muchas gracias.
Thank you,
O sea,
profesora
cierran
Luz de
que
Teresa.
hay una cosa chistosa.
Sí. Sí.
O sea, triángulo equilátero, donde las masas son donde hay una masa dominante y las otras dos son chiquitas. Pasa, por ejemplo, con el Sol, que es muchísimo más grande que Júpiter.
Sí.
Y que Júpiter también es muchísimo más grande que unos asteroiditos. Entonces, si te vas y te fijas en el lugar donde hay un triángulo equilátero en el plano de la órbita de Júpiter, ¿no? Hay 2. Bueno, esos 2 lugares están llenos de asteroides. O sea, son piedritas que llegaron ahí y se quedaron ahí porque es estable.
Estable, ya.
Y entonces esos asteroides tienen un nombre: troyanos, los que van como adelante de la órbita, y espartanos, los que van atrás, o al revés, no sé quiénes van adelante y quiénes van atrás, pero es como muy chistoso eso.
Thank you a lot, Professor Renato Iturriaga, for your amazing talk.